Okay, so we've said to find the real zeros of a polynomial function, we're in section 5.6, we're going to need to understand the factor and remainder theorem. The remainder theorem is what we'll primarily use where we use synthetic division to find the remainder. We said we're going to use Descartes' rule of signs to find out how many positive and negative zeros to expect. And the last theorem we need to find the real zeros of a polynomial function is called the rational zeros theorem. Let's break that down. Rational. What are rational numbers? Rational. Those are the ones that can be written as a fraction. Of course, that includes numbers like 5, because 5 over 1 is a fraction, but it also includes 2/3 and 1/2 and all those. Okay, so the rational zeros theorem says that if f is a polynomial function of degree 1 or higher in this format, so notice the highest power is n, and then the next lowest and the next lowest and the next lowest, all the way down to a constant, where the first one can't be 0 and the constant is not 0, where each coefficient is an integer. Okay, so each a in here has to be an integer, not fractions. Okay, the rational thing we're going to find are potential zeros, but these have to be integers. Then, if p over q in lowest terms is a rational zero of f, then p must be a factor of a sub 0 and q must be a factor of a sub n. So we're looking for factors of the constant, factors of the leading coefficient, and we're going to use those p's and q's to form fractions. These will be potential zeros for our polynomial. They won't be definite zeros, but when you think of all the possible ways we could divide this looking for factors using synthetic division, we don't want to just be left out there trying to use every real number we can think of. So if we get a list, at least we have a list to work from. So this will give us a list to work from for our synthetic division. We'll also know how many positives and negatives we're looking for. So for example, if there's one positive and we find it, we would not look for any more positives because we know there was just one and we already found it. So that's how this is all going to come together. All right, so let's try example 3, where we try using the theorem to get a list of potential rational zeros. Now, this will not give us any zeros that are not rational. What would that mean? Well, like we could have a zero that's the square root of 2, but this won't give it to us. But if we can get all the others, perhaps we'll be able to get that through some other way, like using the quadratic formula or something. Okay, so what we need are all the, so we need to find the all the p, and I'm going to make a note. You don't have to do this every time, but for you to look back at this and remember what we did. Remember, p are the factors of a sub 0, and in this problem, that's the constant, -12. So I just want to list here all the factors of -12. Okay, well, I know I could have 1 times -12, and -1 times +12, and 2 times -6, and -2 times +6, and 3 times -4, and -3 times +4, and a shorthand for all of that is to just write, well, I need plus or minus 1, I need plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Those were all the factors I just named. Now, you don't have to do it in this order. I could have put the 1 next to the 12 and the 2 and the 6 and the 3 and the 4. That's fine. I just kind of like to put them in numerical order, but that would work just as fine. All right, so that's what P is. Remember, we're going to form these fractions. Q are the factors of a sub n, the leading coefficient. What is our leading coefficient? It's 3, right? So that's easy. That's a prime number. You can multiply -1 times -3 and +1 times +3. So plus or minus 1 and plus or minus 3. Now, I just want to carefully go through putting all of these as a numerator and these as denominators. So I like to just say this whole list over plus or minus 1 is basically this whole list, right? So plus or minus 1 over plus or minus 1 is plus or minus 1. And plus or minus 2 over plus or minus 1 is plus or minus 2, etc. So I get all of those. Now I have to take all of those over plus or minus 3. So plus or minus 1 over plus or minus 3 is plus or minus 1/3. And plus or minus 2 over plus or minus 3 is plus or minus 2/3. So see, these are all rational numbers. And, okay, so I've done 1 over 3, 2 over 3, plus or minus 3 over plus or minus 3. Well, that's just plus or minus 1, so I've already got that. Plus or minus 4 over plus or minus 3, I don't have that yet. Plus or minus 6 over plus or minus 3, well, that would be plus or minus 2. And plus or minus 12 over plus or minus 3 would be plus or minus 4. So this is it. What do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9 twice. So we have 18 potential zeros. No other, if this has any other real zeros, they're on this list. All the real zeros are in this list that are rational. Like I said, if it's a square root of 2, it's not in the list. But we hopefully can find all the others and then identify the square root of 2 later, after we've factored out all the others. Now, again, remember we'll also be knowing how many positives, how many negatives. What if it said there are no positives? What if there were no sign changes? Then we wouldn't even bother with the positives here. We would just start using synthetic division and dividing by the negatives. Okay? But we've definitely limited the entire real number system down to these 18 possibilities, and then we let Descartes help us determine which ones we want to focus on. Once we found the one positive, for example, we stop looking at positives and we look for negatives. Okay, so let's summarize our steps for finding the real zeros of a polynomial function. First thing, we're going to use the degree, the highest power, to determine the maximum number of real zeros. To know how many we're looking for. We're going to use Descartes' rule of signs to determine the possible number of positive and negative real zeros. So we'll know how many of each to look for. Then, if the polynomial has integer coefficients, we'll use the rational zeros theorem to identify those rational numbers that could potentially be zeros, like that list. Then we'll use substitution, synthetic division, or long division. Well, we're going to use synthetic division to test each potential rational zero. Each time we find a zero, and thus a factor, we will then have what's left. After you factor that factor out, we'll have what's called the depressed equation. So it'll be 1 degree lower, and we'll continue with this synthetic division on this new equation that we have left after we pull out that factor once we find a factor. Now, it says, in attempting to find zeros, remember, if possible, you want to use other factoring techniques if you can. So if we get it down to 4 terms, instead of using synthetic division, we might try factor by grouping to see what those factors are.